Well, we're going from philosophical discussions to very specific science now. And this is kind of a tricky day because the language will be different than some of that you're used to. So far, we've learned that you don't have to know much about quantum mechanics to do spectroscopy. You just have to accept a few rules. We dealt with rotations and vibrations, which just involve the motions and positions of the nuclei. And the shape of the molecule tells us the rules, basically, that we have to use to compute the energies of the states and the transitions that are allowed, and therefore what the spectrum looks like. So even though spectroscopy is positions, strengths, and shapes, we spend a lot more time learning about where do those positions come from, much of which you don't really need when you go to start using this stuff. Then we spend a lecture learning about the quantitative aspects, that is, the Einstein coefficients are the basis of the strengths, even though we have different units. And then we learned that you can't neglect the shape of a line, especially if you're using a narrow line with laser source, because it might just be monochromatic and parked in some part of the line. You have a different set of problems, by the way, when your laser source is spectrally broad. It's illuminating the entire line, and so you have to think about line shapes when you do those evaluations. All right, so what we're going to do now for the next 50 minutes is we're going to introduce the role of the electrons. The electrons also have angular momentum, and quantum mechanics is largely about angular momentum being quantized, which then leads to energy levels, energy states being quantized. What kind of angular momentum can the electrons have? Well, they move in space, they orbit around a molecule, and what counts is the orbital angular momentum about the a-axis, but they also spin about their own individual axis. What we won't talk about, maybe I'll mention it briefly, is that the nuclei also spin, but we usually just put that aside and don't talk about it. But it comes into play at some level when you get into the strengths of lines. So we're going to introduce the role of electrons, and we're going to do it for diatomic molecules, and we're going to introduce the notation that you have to have. This is the compact accountant type notation for how we can understand a lot by a small set of symbols. And then I'm going to introduce you to the 4 most common molecular models. Remember, models are approximations to reality that are helpful to us. They help us understand things. They guide us, but they're not exactly real. And we'll do this kind of some introductory ones first, and we'll improve that a little bit, and then I'll tell you, summarize by saying, of the things we've learned, what is it you have to know or be able to execute in order to make a quantitative assessment of absorption. On the right is the so-called four-track parabola. So when you see this word four-track parabola, it usually means a parabola that reflects the positions of lines plotted versus frequency, which is wave numbers, typically divided into 2 half planes. This is positive m and this is negative m, where by definition in the p branch m is minus j. So j is always a positive number, but m can be negative and help us make this plot. So usually you have an R branch and a P branch. You sometimes have a Q branch. But for electronic, in contrast with the rho vibrational spectra, where B, the rotational constant, changes only a little bit when you change V. So a rho vibrational transition with delta V of 1, there's a small change in B. And we use that equation, BV is equal to BE minus alpha B plus a half. Now when we go to electronic molecules, we have different potential wells. They can have quite different minima RE, and therefore quite different moments of inertia, quite different values of V. So what that means is that we frequently see band heads. And they'll be at low values of J or M, so you'll see them. Usually you never see them in the infrared, even though they could be there. So that's what we're going to do in the next 50 minutes. The term symbol is the thing that we start with. This is and it can be a little bit more elaborate than this, but right now there's atoms and there's diatomic molecules that we'll talk about. They have the same general format. There's a superscript, a subscript, and a central letter. In the case of the molecules, we use the Greek symbols. In the case of the atom, we use the English alphabet. We'll have L and J. In both cases, there's a 2s plus 1, which will have some meaning. So there's some letters here, S and lambda and omega and L and J, and they have meaning, compact meaning. So lambda, although it's a vector, we treat it as we're only concerned with the projection of the orbital angular momentum. So this is the electron orbiting about the A-axis. It's got orbital angular momentum. And it turns out that we only really care about the projection of that vector onto this axis. That's the so-called good quantum number. So the magnitude of this quantity is always integrals of h bar, Planck's constant over 2 pi. And now there's a symbolism. Just like we have the alphabet soup for O, P, Q, R, S for delta J, we have some symbolism and notation for the value of lambda right here. This is the projection of the orbital angular momentum, and it can be 0, 1, 2. And so we call that, therefore, and we call that then in the alphabet soup, sigma pi delta. On the atom side, it's SPD. So the minimum value is 0. So over here it's L, that's for an atom now. Over here is for molecule, 0, 1, 2, sigma pi delta SPD. So that's the essence of the lambda part of this. S is related to the spin, and we only deal with the spin of the electrons which are in unfilled shells, the outer ones. The spin of an individual electron is 1/2, but we have to allow them to sum up in a certain way. But S, the magnitude of this vector will be S times the h units, and it has to have half integer values, meaning it could be half, or 3/2, or 1, any multiple of a half. If the shell was closed, there wouldn't be any electrons out there, and there wouldn't be any spin. What's sigma? Sigma, in contrast with this sigma right here, sigma is the vector sigma, is the projection of S onto the same A-axis. So lambda is the projection of the orbital angular momentum. Sigma is the projection of the spin angular momentum onto the A-axis. And it turns out that this is only defined when lambda is not 0. So it's the same thing, multiples of h bar. And it has allowed values. And so it will have as allowed values S minus 1, 2s plus 1. So if S is 1/2, 2s plus 1 is 2, there's 2 allowed values of sigma. Basically plus and minus, forward and backwards along the axis. Omega, down here in the subscript here, so up here J, you know now, that's the total angular momentum. Omega is also a sum. It's a sum on this A-axis of the two components. And so it is the sum of these two vectors, and we do this just to remind ourselves that it can be plus or minus. And it can take on values that range from lambda plus S down to lambda minus S, as long as lambda is equal to or greater than S. So it looks kind of complicated, but usually there's only a couple of values here, and they're expressed in the form of numbers, and you'll see. Let's look at some examples. Nitric oxide. Nitric oxide is actually a fairly complicated one. The ground electronic state of NO is x2 pi. Now I've added an x. The first thing that appears is a capital letter. X denotes ground state. That's the lowest state. If it were the first upper state of the same multiplicity, we'd have a capital A in front. So that X tells me something. We're talking about the ground state of NO, not the first excited state or the second. Now, S is, the 2s plus 1 tells you that S is 1/2. The pi tells you that lambda is 1, and therefore omega can be either 3/2 or 1/2. And these two states, sometimes given different names, are called spin split states. So there are two electronic states. There's the 2 pi 1/2 and the 2 pi 3/2. So there's two 2 pi states. And you could have guessed that by looking at this too, and the reason that we call it the multiplicity. So there's going to be two of them. And it's hard to say exactly what the energy spacing between these states will be, but in this case it's 121 wave numbers, which by multiplying by 144 you get a sense as to the characteristic temperature. What about CO? CO is a nice one. The ground state for CO is x1 sigma plus. We're not going to talk anything about the plus. There's some pluses and minuses and U's and G's that appear that are at a little more complicated level that we don't need to deal with. The key is that the ground state is X, and it's a 1 sigma state. What does the 1 mean? Spin is 0. That is, there's no net electron spin contribution. There's no angular momentum that I have to worry about. Similarly, lambda is 0. Oh, there's no orbital angular momentum I have to worry about. Forget the electrons. They don't do anything. And so we call this molecule, that is a 1 sigma, we call that a rigid rotor molecule, because when you see finally the energy level expressions for rotation, they're exactly the same ones you've already seen. In other words, in a 1 sigma case, we don't have to worry about the electrons. That's nice. It's the easiest case. Well, oxygen is a pretty important molecule. It's an X3 sigma. We'll forget the G in the minus here. The 3 tells me that the spin is 1. There's 2 electrons kind of net in one direction. Lambda is 0. Oh, that's interesting. There's no net orbital angular momentum, but there is spin. And when that happens, it's a certain category that we talk about. And we're going to call that Hund's case B. So Hund was some famous fellow who came up with several candidate cases, and he called them A, B, C, D, E, F, etc. We're going to deal with A and B. So these are 3 molecules we care about in combustion, and they're all 3 different. We could have dealt with the row vibrational spectra with what we had already for the most part. But now when we get to the electrons, it starts to get different. So here's our four simplest models. The rigid rotor, for which lambda and S are both 0. The symmetric top, where lambda is different from 0, but spin is 0, so these have no net spin. These have spin down here. One has lambda and one doesn't. Those are kind of the 4 primary categories. This says today's lecture. That should have been the first lecture today, is this, and then we'll deal with this, we'll recap a little bit, and then we'll do some Hund's case A and B. And we'll sail through all of this in 50 minutes so that you'll at least have seen this. And sometimes I'll go too fast, but you've got the notes so you can study it later. The rigid rotor, a 1 sigma. So if I look in the Janov tables or Hertzberg and say, what are the electronic properties of the ground state of CO, you'd find out it's a 1 sigma state. And that means that we could represent the molecule like this. We have the usual A axis. We have the perpendicular B axis equal to the C. We have to worry about the rotation of the nuclei about B, but there's no electrons in the problem. So this omega, which was the combination of 2 vectors, is 0. It's not defined. So there's no projection of any orbital angular momentum onto the A axis. The only rotation, and therefore the only angular momentum we have to worry about, is the one we've already dealt with of the nuclei. So life is good when you see 1 sigma. Now let's go to the rigid rotor. Rigid rotor, spin is still 0, so 2s plus 1 is 1. The sigma, that's the rigid rotor, excuse me, I'm getting ahead of myself. So here's our energy expression where we forget this one right now, that's the correction term. It's the same as before. The energy now is always the sum of electronic, vibrational, rotational, and so you have to add up whatever the electronic term energy is, by definition 0 in the ground electronic state. Plus, and that should be a V. So whenever you see a quantum number, it's V, not nu. Sorry, yes?
Well, there's no translational?
Okay. When we deal with spectroscopy, we're dealing with the internal energy states.
Okay.
So we think of this, the translational motions are also quantized, but the spacing is so narrow we don't think about it. So the lines we see are associated with transitions in the internal energy states, not the translational motion of the molecule. We have to worry about the Doppler effect when it's moving, but okay. Now we always have selection rules. So now for our 1 sigma state, it's a rigid rotor. We have exactly the same rules we've had before. A P and an R branch, we're basically done. Now, I do remind you that sometimes people use different rules for the different definitions for selection rules. I define delta J to be J upper minus J lower. So it can be plus or minus 1. Sometimes people do different definitions. Okay, let's see. Oh, I think I left out this. Okay, now I should talk about the Pier Rotations is delta J is 1 because it's J upper minus J lower. The rho vibrational spectrum, we had delta V could be 1, only plus 1, and then delta J is plus or minus 1, so there's P in an R branch. Now, what about the rho vibronic spectra? That means the combined electronic transition, electronic change, vibrational change, rotational change. I've got to bring in the electronic energy. It'll turn out that the delta J is going to stay the same, but this one changes. And that introduces what's called the Frank-Condon factor that I tried to explain in words. But you're going to find out that delta V can be any integer, plus or minus, that links one state and another. They occur to varying degrees, and they're defined in a way that the sum of the Frank-Condon factors will be 1, but it tells what the splitting is between all the possibilities. And that we try to explain with the Born-Oppenheimer principle, but we end up looking at tabulations for this. Okay, what about the intensity distribution? So I want to imagine now a plot of the line strengths of the individual lines in the P and R branch. There's the R branch, there's the P branch. The simple idea that I introduced was the so-called equal probability idea that the strengths of the lines are nothing more than the Boltzmann fractions. That's not exactly right. And the correction to that is called the Hanel-London factor. And you'll see it. So there's a slight correction to my idea. It's the Boltzmann distribution with a multiplier. And these relative intensities between the candidate vibrational bands, we're going to get that through what's called the Frank-Condon factor. And we'll see how that's defined. But the main thing is the Boltzmann distribution that tells us how the states are populated. And let's see. Now, if we look at a lot of different diatomic molecules, that's what we're doing right now. The ground state of the diatomic molecules, CO, chlorine, bromine, nitrogen, hydrogen, they are all rigid rotors. What does that mean? They're all 1 sigma in the ground state. And it turns out that, remember, we have sigma, pi, delta. So the pi means that that lambda value is 1. It turns out that there, as far as I know, there are no ground state diatomics that have delta. So in other words, that lambda value is either 0 or 1. The 2's don't seem to exist for ground states of these molecules. So that's kind of nice to know. But some linear, okay, so there's none of those. Now, linear triatomics, which we treat as just a little bit more complicated than the diatomics, are handled a little bit differently. One of the things you'll notice is that you start seeing this little tilde sign on top of this state. So the ground state would be an x1 sigma g. For CO2, it looks quite a bit like CO. It's x1 sigma, but there's a tilde that's telling me that it's triatomic. And HC and N2O. So they also are rigid rotors. Good. But I'll just mention here, for symmetric molecules, you have to worry about nuclear spin. You have to worry about the fact that the nuclei are spinning. If it's asymmetric or asymmetric in the structure, you never have to hear the word nuclear spin. But when it's symmetric, because quantum mechanics has rules and statistics, and no two molecules can only occupy certain states, it turns out that that spin comes into play and explains why we see variations in the intensities of the lines due to this nuclear spin. I don't think we're going to talk about that in here. Okay, symmetric top, that's the next one up. Diatomic molecule, there's lambda. It's the component of the orbital angular momentum along this axis. There's N. Okay, now, when J is always reserved for the total, since there's now a contribution from the electron orbital angular momentum, I have to pick a new symbol for the motion of the nuclei about the B axis. And it's labeled as N, typically called N. Remember we had K for when we introduced J and K? This is now we use N. So this model is quite a bit like that one when we did the rotation of the symmetric top. You have two components of momentum you have to combine into a total. So when lambda is unequal to 0, but S is 0, you have this case, the symmetric top case. And those states would be 1 pi, remember now lambda is say non-zero, but you have to either have a lambda, you can't have a sigma, it's a lambda or a delta. Although I've just told you that for diatomic molecules, we never have a ground state delta. So we've introduced the fact that we now have to give a new name to the nuclear motions and their angular momentum. J is always conserved. It's the vector sum of these two contributions. Turns out that in a quantum system like this, you only have to worry about the axial component of this angular momentum, and that's the one that's quantized. So I don't actually know the orientation of this vector. We only have to worry about this component right here. It's the so-called good quantum number. Okay, symmetric top, here are our constraints. Now we have the rotational energy expression you've seen before. B, jj plus 1. We use F always for rotation. Function of j plus a minus b lambda squared. Lambda is a number, it's just a constant. So this is therefore only a function of j. So it's the same spacing as a rigid rotor, but with a constant offset of a minus b lambda squared. A and b have the same meaning they've had before. I sub A is small, it's a diatomic molecule, so A is really much bigger than B. And lines with J less than lambda are missing. So J has to be at least as big as lambda because J is a sum of lambda and N. Okay, selection rules. Selection rule now for an electronic transition, so we have to be a little careful. Delta lambda is 0. Delta J can be plus or minus 1. Delta J of 0 is allowed, but it's extremely weak, so let's pretend it's not there. But if delta lambda plus or minus 1 also is allowed, and in that case, delta J can be plus or minus 1 or 0. So in these cases, you have a Q branch. In this case, you have only the P and the R. Now, because you have this Q branch, and because we have potential for big differences in the moments of inertia between the ground state and the upper state, you can see multiple band heads, typically. Okay, symmetric top. What does the spectra look like? So now, symmetric top means I've got to have lambda unequal to 0. So it's got to be either 1 pi, or 1 delta, 1 delta. S is 0, so I can only have 1s. And lambda is unequal to 0, and I'm only allowed to consider right now a 1 and a 2 here. We've already got the expression. Now, T prime, that's the energy of the upper state. So I've got an electronic state that I haven't really characterized, except I've said delta lambda has to be either, you're going to learn delta spin is 0, but delta lambda can either be 0 or plus or minus 1. So I have the energy expression for the upper state and the energy expression for the lower state. If the lower state was the ground state, that term right there would be 0. And so we get the frequencies of the transitions by taking the differences in the energies. And I can have expressions for P, Q, and R that look quite a bit like the ones you've seen. When we did this for rho vibrational, this difference right here was minus alpha. But now we have to worry about the differences in the moment of inertia. This could be a much bigger number, and it could be plus or minus. So these are the energy level expressions that look quite a bit like the rigid rotor, but with this other stuff on there. Remember our definition of, we use M to be either a minus number or a plus number this way. And you're going to see later why we like this. And these expressions follow this format of a constant called the rotationless transition number plus AM plus BM squared. So they're always of this form, a linear term and a square term. Where A, did I do that right? Where A, I'm questioning now in my mind whether that's supposed to be B or not. I'm not really sure. Where A is the sum and B is the difference in B's. So when you plot these lines, they look like this. So this is a symmetric top for delta lambda of 0. And this is what they look like. There's the band head. So if you took an exposure on a piece of film, the last line would be right here. That would be the band head. And the last line of the Q branch should be right here. So you'd see two apparent band heads. There's also some lines that are missing lines near the origin here because you have some rules. Depending on which branch you're in, there's some minimum value of M, because you have to have J. J has to be a positive number. It can't be 0 in this case, because we have a value of lambda that's 1 or 2. Now, so these are the positions of the lines. Now the question is, what are the strengths of the lines? And I'm going to show you that we have to introduce this new thing called the Hansen factor that is typically written, unfortunately, as a capital S sub J. So we have capital S for line strengths, and we have capital S for Hansen factors. You'll see what they are. And then the superscript tells us whether we're applying this in the P, Q, or R branch. And this is the breakdown to my principle of equal probability. These are my words. Nobody else has ever used them, I think. But it helps people think about these line strength distributions. Okay, now we're going to look for this symmetric top. And remember, we had two possible selection rules for delta lambda. Delta lambda of 0 and delta lambda plus or minus 1. Let's look at the case for delta lambda of 0. And therefore, and this is the Hansen factor. You look it up. It's in the table. What's lambda? Well, it's going to be 1 or 2. What's J? Well, it's all over the place. Ranges maybe from 1 or 2 up. Let's look at the case where J is large. So forget the lambdas. So this Hansen factor is approximately J plus 1. This Hansen factor down here is approximately J. This Hansen factor right here is approximately 0. Because I told you earlier that the Q branch is very, very weak for this case. What's the sum of these things? 2J plus 1. So the Hansen factors are designed so that they sum to the degeneracy 2J plus 1. But you think about it another way. This is the fraction. This is like a fraction. So if you're in a given state and you look at emission down to two possible lower states, P and R, this is the relative strength. And this is why the R branch is slightly stronger than the P. It's stronger by the ratio J plus 1 to J. That explains what we've seen before. Okay, so it's usually, not always, defined so that the sum of these Hansen factors is 2J plus 1. That leads to some simplifications. So remember, the total degeneracy is 2J plus 1. And so the amount that goes one way is J plus 1, the other way is J, so it's like a fraction. So you're going to find out that you can think of this like a fraction. And we're going to find some simplification when we think that way. But there's another possibility. Delta lambda can be plus or minus 1, meaning that it's allowed. When you look up these factors in Hertzberg, for this case, you'll see these expressions. That in the limit of large J relative to lambda, the R branch is 2J plus 1 over 4. The P branch is 2J plus 1 over 4, and the Q branch is twice as big. So for a 1 delta to 1 delta electronic transition, the strength is mostly in the Q branch. Whereas for the delta lambda of 0, meaning that you go from lambda of 1, say, to lambda of 1, there's no Q branch, basically none. Just rules. And if we follow the rules, we don't have to know too much quantum mechanics. Second example. If x is 1 pi, so now we're being specific. The ground state is 1 pi. And now if we apply delta lambda of 0, then the upper state is also 1 pi. But if we take plus or minus 1, so there are 3 possible outcomes. Now remember, when you do molecules, you put the lower state on the right and the upper state on the left, and the arrow tells you which way you're thinking about it. So we're starting in the ground x1 pi, that's here, and here, and here, and we're transitioning to the 1 sigma, or the 1 delta, or the 1 pi. Because there are 3 possibilities. 3 different electronic groups of lines. I call them systems here. but in quotation marks, because in principle the word system should correspond to all of the electronic transitions from one electronic state to another. This is like 3 separate subsystems. I probably should have used subsystems. And the Hanson-London factors are quite different for this case than for these. Just rules. They're all spelled out. So if you have a symmetric top, you follow these rules. If you have a rigid rotor, you follow those rules. If you have a Hund's case A, you follow those rules. What's a Hund's case? And so these are 4 different cases. They're 4 different approximations. Hund's case A. So these now, we're going to look at these 2 that have spin. These first 2 have no spin. One has no lambda, one has lambda. These 2 have spin, one has lambda, one doesn't. Then there's a last little complication I'm going to tell you about called lambda doubling. Here's the picture of Hund's case A and Hund's case B. Hund's case A has lambda. There it is. Hund's case B has no lambda. If there's no lambda, what is lambda? It means that there's orbital angular momentum about this axis. And when you have current that's flowing around, you have a magnetic field, like along the axis. That magnetic field tells the spin that it has to follow some rules. And so when there's a magnetic field, as there is here, there's some constraints on the, when there's a magnetic field, there's constraints. That was the symmetric top. When there's no magnetic field, S can do its own thing. That's N here. We always have N. So there's a difference then between Hund's case A and Hund's case B in terms of the constraint on the orientations of the spin. So there's 4 cases. There are more, but these are the 4 primary ones. They're models. They're approximations to reality. When we actually look at the spectrum of a given molecule like OH, NO, CO, it may follow these models really, really closely, or they may not exactly. But this is the way we think. All right, this is a review. Term symbols are important. 2s plus 1, lambda, omega. Integral values of these things. Lambda can be 0, 1, or 2. For ground state, we never see this one. And the symbol is sigma or pi. We do see some deltas, but they would be not in the ground state. And so a lot of the definitions are buried on this page. 4 models. 2 with spin, 2 without. 2 with orbital angular momentum, 2 without. Oh, and let's see. I should say. So a lot of molecules that we like, nitrogen, hydrogen, CO, are rigid rotors. Some other molecules that we care about in combustion are Hund's case A. They're 2 pi, x2 pi. So both OH and NO are x2 pi. That is, the ground state x is 2 pi. 2 pi says that the spin is a half, and there are 2 solutions. There will be a 2 pi 1/2 and a 2 pi 3/2. That'd be 3/2 and 1/2 down here. Hund's case B applies to oxygen. Oxygen is x3 sigma. So it has, what does that mean? The spin is 1. So that turns out to have a different set of rules. We'll see. So let's see. So the electrons are orbiting around the A-axis, but we only really care about the component along the axis. That's the distinction now between capital L, vector L, and lambda. The explanation for that is that only lambda is a good quote-unquote quantum number. We don't care about the L. Now, this could be, of course, plus or minus, so you have to be careful. It could be pointed this way or it could be pointed this way. So if this was NO, it could be pointed this way along the axis or it could be pointed along the other direction. And because of that little subtlety, that's called lambda doubling, lambda can be pointed either way. And that turns out to cause a slight separation of the lines called lambda doubling. Okay, spin. We get the spin by looking only at the electrons outside of the closed shell. if there's an even number of these electrons that pair up, that's an integral. It's an integral. Odd number is half integral. So it's always something like 0, 1/2, 1. It goes like that. But sometimes we see an integral. An integral means that they're paired up. Only when we have orbital angular momentum do we have the current, which gives us the magnetic field, which locks S down. So we only really have this locking of the S onto the axis when lambda is unequal to 0. Okay, this is a lot of stuff, but there are just rules. You just have to learn the rules and follow the rules. Okay, remember that omega is the combination along the internuclear axis of the two contributions. So what have we done with electrons? We've recognized that they have spin angular momentum and they got orbital angular momentum. And we've got to pay attention to both of them. And they combine in certain ways. So we're adding that to the angular momentum of the nuclei. This is my simple explanation here. If lambda is equal to 0, there's kind of an implied magnetic field along this axis. The current is running around the axis. That implies a magnetic field which locks down the spin of the electrons. They feel that magnetic field. And as a result, they feel that magnetic field and it affects their energy. This is a simple approximate expression for in the electronic energy of the molecule owing to this effect. So there's some base number plus A lambda sigma. Well, lambda and sigma are the things I've just defined. They're the magnitude of the component along the axis. If lambda is 0, then there's no effect. Or if sigma is 0, there's no effect. So this only occurs when they're both present, and this is called spin-orbit coupling. Turns out that this A multiplier here can be either plus or minus. And so, for example, if you have NO has this character. NO can be either 2 pi 3 halves or 2 pi 1 half. And if A is positive, then this state is a little higher in energy than this one. If A is negative, it's inverted. It turns out OH is inverted. NO is positive, is regular. So it's possible for this number to be negative. But all it's really saying is, what's the difference in the energy levels for these two spin-orbit substates? So we got an NO molecule. It's in this grounded electronic state, but it has two configurations. You could think of these as each one is a separate molecule. They have the same moments of inertia. The B's are the same, but it's like two molecules that exist together that are very, very similar, but they're shifted by 121 wave numbers. So it's like two very similar molecules. And this is we're kind of continuing on this theme of how the orbital angular momentum and the spin angular momentum couple together in different ways. So here's a case where I have both of them. And I need both of them in order to have that splitting that I talked about in that equation. Called spin splitting. Remember, these are just models. And one more complexity. Sometimes you find that when the J is small and it's kind of lazily rotating, one model applies, and then when this thing's spinning like crazy, another model applies. So sometimes when you range from low to high values of J, it switches from being like one model to more like another model. And this happens to be the case for OH, unfortunately. So what does that mean? That means when you model a spectrum, you have to use a little more complicated, you have to use a mixed model. They're already in the literature. You got to read it and program your computer to calculate the lines. Interactions. So now, let's imagine we have a 3 delta state. Spin is 1, lambda is 2. Possibilities are 3, 2, 1. So the spin stays fixed, but the way that they can combine, there's 3 outcomes. Notice that multiplicity, they call this the multiplicity, and you can see why. There's 3 answers. So these are the 3 electronic substates that you can have for a 3 delta system. They're going to have slightly different energy. we can go back to our approximate equation and we can see how this applies. So here B. So here we have a 3 delta where S is 1, lambda is 2. Now we have to pay attention. This sigma now can take on 3 different values. Sigma, it's 1, but it can be 1, 0, or 1. So we're talking about the component along this axis, and it can have 3 values. Therefore, this 3 delta state actually has 3 substates. So when A is greater than 0, this one is up here higher than this one and this one. And the splitting is 2A. So whatever that A is, that's kind of a measure of the splitting that you're going to see. You can look in the tables and say, oh, A is 100 and A is I think it's about 100 and, it's a negative number for OH. I think it's like 140. So it's some number of wave numbers. But those numbers are bigger than the width of a line, which is at atmospheric pressure, 0.1 wave numbers about. So line widths are of the order of 0.1 wave numbers. Now all of a sudden, and the spacings are 10s, 20s, 30s. So even for the same apparent rotational numbers, the lines appear in the space. It's like there's 3 molecules. Very similar molecules, but they're different. Oh, here's some examples. I should have used this. Yeah, OH is about minus 140. Look at the range. So beryllium hydride, little teeny number. Mercury hydride, 3600. So the magnitude of this effect ranges over quite a range. That's called spin-orbit splitting. Splitting between the spin, the coupling between the spin and the orbital angular momentum comes into play. Doesn't change the value of B. That's just based upon the moments of inertia of the nuclei. So now we got to consider the case where S is, now we're going to Hund's case A. So Hund's case A, both of these are non-zero. Both non-zero. Here's our, and now since they're both defined, this is really another symmetric top molecule. So it's the rotational energy is B, JJ plus 1 plus this constant correction term. Although we have to be very careful what we're meaning here by A. It's a little subtle. We've used capital A for H over 8 pi squared I sub A and B. This A is not exactly the same thing, because it was introduced as the spin-orbit coupling constant. So we have to be careful sometimes about the notation. There's going to be 3 branches, P, Q, and R. Here's an example then. So the 2 pi, and my best examples are like NO and OH, are 2 possibilities. Now that means that each one of these substates has 3 branches, P, Q, and R. So taken together, you're going to see 6 branches to a given band of, say, the A to X system of NO or OH. You're going to see 6 branches. Why 6? Because there's 2 substates. Each one has 3 branches because of the selection rules that give you both P, Q, and R. So it starts to look pretty dense. Hund's case B. This one is really kind of simpler, and it's a common one. It's oxygen. So this is when the spin is not coupled. So when lambda is 0, there's no magnetic field, there's no coupling. S does its own thing. So here's S somehow out here. N is always perpendicular, J is the total. Now, we still have some rules. J can only take on allowed possibilities. If S is 0, well, if S is 0 and lambda is 0, we don't use an N, we just use J. But we will have N plus S minus 1 down to N minus S, meaning we're going to have 2S plus 1 terms. So here's a good example. This is oxygen. So when I say, this is the ground state. So now I'm only showing you the energy level structure of the ground state. I haven't shown you the upper state. You got to do both in order to take energy differences. So the problem is going to get doubly hard in a minute. But you have to do this to each state. Now there's a notation, there's a rule for everything. So F is the rotational quantum number, and we can write this either in terms of N or J. It's common to do it as N. Now the question is, what's J? There's F1, F2, F3. There's 3 possible values of J. J can be n plus 1, n, or n minus 1. If I'd have done it in terms of J, there'd be 3 values of n. So for n of 2, for example, J can be 3, 2, or 1. They have slightly different energy. The way I remember it, you only have to remember one thing. I remember that F1 is always J is equal to n plus. So if S is 1, as it is for this case, F1 is J equals n plus 1. Then the others follow. You don't have to remember all 3. All this is doing is saying that it's no longer enough to specify n. You've also got to specify whether it's the 1, 2, or 3. Because these states have different energies, and then the upper state has different energies, and when you take the difference in these, you get different line positions. All the work almost goes into line positions. Now there's a little trick down here. When n is 0, what's the allowed value of J? Well, you have a spin of 1, so you cannot have negative, you can't have 0J in this case, and you can't have negative J. So the only value of J you can have is 1. So even though n is 0, spin is 1, you've got to have that appear in the J. So sometimes there's missing energy levels that you have to pay attention to. Okay, the last complication. Good. I finally found my substate. I got n, I got J, I got everything. But unfortunately, lambda maybe can be plus or minus. And that little teeny splitting right there is called lambda doubling. Usually you can't see it. By definition, F is split into a C state and a D state. Usually this is too small to see, but it's there. What's the degeneracy of this state? I gave you a clue. I said the degeneracy of that state.
0.
2J plus 1. 0. I've never heard that answer before. So because we haven't removed the possible role of the... Now I have to be careful. I think it's 2J plus 1. There's always this fact that we call it a... I should have really said level. There's this unresolved role of the degeneracy. It's the number of states with the same energy level that you can't resolve because there's no field present to cause it. So at the end, you're always left with this 2J plus 1, unless you got the field. Why do I care so much about the degeneracy? You're going to see when we try to get quantitative, we have to pay attention to this. By definition, usually the C is the one that's on top. It's usually very small. I just want to mention it to you. It affects the distribution. Change of parity. Okay. That G and that U the G and the U and the plus and the minus that I say don't worry about it, comes into play when we talk about the allowed transitions. In the end, there's like a whole bunch of energy levels, and you want to know which ones are connected. And there's a restriction on the ones that are allowed that is controlled by what's called parity. It's one of those symbols. So once you see the symbol and you know the parity rule, you know what to do with it. But otherwise, did I skip something there? I don't know. Okay. All right. We're basically almost done with this. What I want to do is bring it back to reality. What do we have to know to do quantitative absorption? Here's Beer's law. What's K? Here's K. The line strength, sometimes called intensity, or integrated absorption intensity. Line strength, that's not the London factor. 1 to 2 tells me I'm worrying about the transition from 1 to 2. Here's my line shape. Now I'm going to rewrite S this way in terms of the oscillator strength. So this is a number. This is the number density in level I. Number per unit volume in level I. The oscillator strength, it's a number. This is a 1 minus. This term is usually 1. That's K. I need to know S and I need to know phi. We talked about line shape. How do I get to S? It's just a number if I tell you the oscillator strength, there's only one thing left, the Boltzmann fraction. We think the Boltzmann fraction is pretty simple, but wait till you see how complicated it gets all of a sudden now. But this number is usually tabulated. You just look it up. This is a little tricky, and we're going to spend some time on this. All we have to do to get to quantitative Beer's law absorption or emission is to deal with these two problems. Where do I get the oscillator strength? Where do I get the Boltzmann fraction? Those are the two things that we have to deal with. Let's look at the Boltzmann fraction and see if I can scare you. This is, I think this is almost the last slide. Here's the Boltzmann fraction. The number in level 1 is the, I can't even read my own writing here. Oh, okay, okay, number in level 1 can be thought of as the total number of I times the fraction of I that's in level 1. So this is the total number density of the species here, and this is the fraction in that level. Here's where the trouble is, right here. The fraction in that level depend upon now several quantum numbers. The electronic state, the vibrational level, the value of lambda, and delta, and J, and N. So I got to be careful about these things because I'm trying to identify the fraction in this level. And by this level, I mean the one for which the only remaining degeneracy is 2J plus 1. Electronic vibration. So you have to be careful about all these things. And this is when you say, thank goodness it's a rigid rotor. Otherwise, it's tricky. All right. The oscillator strength turns out usually is not that big of a deal. The oscillator strength for the individual transition that's going to take me from level 1 to level 2 is usually written as this way. This is a shorthand notation. It's really the oscillator strength for going from this set of quantum numbers to this set, or vice versa. It's usually written this way. So sometimes you see F12, sometimes you see J double prime, J prime. It means going from one level to another. Here's the thing that's fun. It's written as the product of three numbers. There's, by the way, there's no units. There's the Hanel-London factor, the Frank-Condon factor, and the overall system oscillator strength. It's a number. This number says that if you're in a given excited state, if you're given a level up here in an excited state A, the sum of all of your possible A's gives you the overall rate of lifetime and gives you F. It's like the total possibility is buried right here. This says that, okay, I'm in a specific V prime. What's the chance I'm going to go to a specific V double prime and compared with all of them? That's the fraction. It's a number. The sum of the Q's is 1, and you just look at this and say, if I'm at a given V prime, 50% of it goes to a specific V double prime. Overall number, the fraction in the band, the fraction in the given line. So it actually has simple meaning. Some of these Q's is 1, some of these is 2J plus 1, which goes, there's one complication here. You have to pay attention to this little correction term. And the sum of these, sum of all the lines turns out to be this oscillator strength. What's the 2s plus 1? This has to do with, like the spin is 1/2. This is the Kronecker delta. What do I say here? 2s plus 1 times delta. Okay, if you have, this is accounting for lambda doubling. So I've got a factor of 2 here, and this is the spin splitting. So that just reminding me that if I'm in a given, and this is a 2 pi, say 1/2, if I'm in a given J, there's 2 n's. There's 2 n's, and there's 2 lambdas. I get a 4. So you have to be careful. Not everybody uses the same notation in some system. All right, so I'm going to sum up. The band oscillator strength would be written with V's. It's the product of FEL times Q, meaning the sum of all of these would be just FEL. So when you see F00 for the OH system, and it's 0.001, that's saying that's all I really need. Now, if I have that number, I just have to multiply by the Hanel-London factor, and I have the strength of my line. So usually it's in a very compressed form like this. So the individual oscillator strength is the band strength times this Hanel-London factor expressed in this fractional form. And so the sum of these is going to be 1. if you have only PNR. So it's not as bad as you might think, as long as you follow. What's easy to do is make a mistake and forget a factor of 2 or a factor of 4. But usually, other than that, it's more straightforward than you might think. Now, some people are very, very, very precise, and they put an additional correction term in here that's always very, very close to 1. But, so you should know that sometimes there's a T, but for the most part, you can neglect it. Then there's some rules about, am I talking about the oscillator strength for absorption or for emission? So there's a little difference between the V double prime prime and the V prime double prime, and they're related by the degeneracies. That's another subtlety. Because usually, maybe they give it to you for emission, but you want it for absorption. You've got to be careful about the G's. Okay, we're going to spend about 50 minutes going through in gory detail how you would do this for OH in the next 50 minutes. And this is like a homework problem that I give in my class. And it's kind of, but like you, they have my notes, so they go through the notes and they try to figure it out. Okay, we'll take a break now and come back. We're supposed to be back at 3:15 or so.